Now, one of the things that we've mentioned so far is that all gases have got roughly the same molar volume. Molar volume is volume divided by mole, so it's liters per mole. And it's pretty much the same value for all gases at the same temperature. It happens to be 22.4 liters per mole if you're at 0 degrees Celsius and 1 atmosphere of pressure. Now, this stricture on the end, these conditions for this to be true, this is called standard temperature and pressure and you'll sometimes see that abbreviated as STP. So instead of saying at 0 degrees and 1 atmosphere, they'll say at STP. Now we can make use of this in a couple of different ways, this little fact right here. We can use it as a conversion factor between a gas volume and moles. So for example, if I had 3.0 grams of H2 gas, and I want to know what the volume of that would be at STP, I could say, well, this is my critical link. 22.4 liters is 1 mole of gas, any gas. So if I can turn grams into moles, then I'll have the liters on the end here, and that will be my link. I can set up the rest of the problem like this. What's the molar mass of H2? It's 2.016. Each hydrogen weighs 1.008, so twice that is 2.016. And then I can use this as a conversion factor between moles of H2 gas and liters. This happens to be about the volume of a beach ball. So a mole of gas, any gas, occupies about a beach ball worth of volume at STP, at standard temperature and pressure. So 3 divided by 2 is about 1.5. So this would be something like 33 liters, something like that. Whatever it's going to be. And if I started out with 2 significant digits here, I'll round off my final answer off to 2. So this is a way to link an amount of gas, moles or grams, with a volume of gas. Now, it also means this. Equal volumes of gas at the same temperature and pressure contain equal moles. Or you can say, if they have equal moles, you can say not just equal moles, but equal molecules. Equal numbers of molecules. This statement has a name. It's called Avogadro's principle. So he has a number, and here's his principle. Let's put a box around that. That's kind of handy. We can use it in doing stoichiometry of gas reactions. What do I mean by that? Here's a gas phase reaction that industrially is very important. It's called the Haber process. And it produces ammonia gas, which is used in agriculture. It increases productivity of a field by quite a bit. That's a gas phase reaction. Everything in it is in the gas phase. And I can use Avogadro's principle to interpret this balanced chemical equation in a new way. We always have been able to say, well, this means it's a recipe. It means 1 mole of N2 gas plus 3 moles of H2 gas gives me 2 moles of NH3 gas. But I can also use it for liters. If equal volumes of gas contain equal moles, I could say something like 1 liter of N2 gas plus 3 liters of H2 gas gives me 2 liters of NH3. So it's like 1 box of N2 plus 3 boxes of H2 is going to give me 2 boxes full of NH3. So I have a volume to volume conversion factor from this. If I interpret the equation just with liters instead of with moles, Avogadro's principle lets me do that. Now, all of these things have got to be gases for this to work. It won't work if they're not gases. This doesn't work if they're not gases either. Different substances, solids and liquids, have much different molar volumes than this. All right, how would I use this little fact? Suppose I had 20.0 liters of H2 gas. And I wanted to know how many liters of NH3 gas could I make from that? Well, I could use the equation as a liter to liter conversion factor between H2 and NH3. I could put liters of H2 on the bottom to cancel that out, and then liters of NH3 on top. And I can use the coefficients in the balanced equation. The same way I would do a mole-to-mole ratio, I can now do a liter-to-liter conversion factor. So this would be 20 times 2 is 40 divided by 3. So a little less than 15, whatever this number is going to be. That's how I would set it up. You have a problem just like this on the worksheet, where it's having you do combining volumes in a gas phase reaction. This technique that we've just done, getting liter to liter conversion factors from a gas phase balanced equation, it's called the law of combining volumes. Sometimes this procedure that we just did, the law of combining volumes. So you sometimes see it referred to that way, and it's sometimes named after the person who found it. Gay-Lussac's law.